Imagine everything you see, feel, touch. Everything you call real isn't what you think it is. Not just a vast, empty void sprinkled with stars and galaxies. Not simply an endless, chaotic ballet of matter and energy governed by unyielding external laws. Imagine something. Colder, quieter, infinitely more precise. Imagine that everything around you, the device you're watching this on, the complex symphony of neurons firing inside your brain, even the fundamental rules that govern how things behave, the laws of physics themselves, aren't fundamental things in and of themselves. Instead, they are the result of a process. Not some random, happy cosmic accident, but a computation. And I don't mean a simulation, not exactly. A simulation pretends to be real. This idea suggests something deeper, something more profound. A process that doesn't pretend to be a universe. It is the universe. Think of it like a quantum computer, one that started running. About 13.8 billion years ago. From that initial, incredibly dense state, it began its work. Every collision between particles, a calculation. Every interaction, a logical operation. Every single moment ticking by in time, a step, an iteration. In an unimaginably vast cosmic algorithm. This isn't just fodder for science fiction anymore. Some leading physicists and computer scientists aren't just entertaining this idea. They're starting to believe it. The universe isn't just like a computer processing information. It is the processor, constantly updating itself, evolving, crunching gargantuan amounts of data every single second. And that ceaseless calculation, that process, that's what turns into the reality we experience. And if that's true, then you, me, everything we perceive, we aren't just made of atoms, bound together by forces. We're made of instructions. You are part of the output. For centuries, we've been taught to look at the universe like it's a vast, intricate physical machine. A collection of objects, atoms, molecules, planets, stars, moving through space, pushed and pulled by fundamental forces, obediently following predictable laws. Drop a ball, it falls. Light a match, it burns. From the tiniest electron to the largest galaxy cluster, everything seems to behave in predictable, measurable, classical ways. It's a powerful picture, and it's gotten us incredibly far. We've built civilizations, developed technologies, and even looked back to the very first moments after that presumed Big Bang using this framework. But beneath all of that apparent motion, beneath the tangible matter and visible energy, there's a growing, persistent whisper among the deepest thinkers in physics and computer science. A feeling that something else might be hiding there. Something far more fundamental. At first, it sounds abstract, doesn't it? Not very physical. We think of information as labels, numbers on a screen, data stored on a hard drive. But in physics, real physics, information isn't just a label. It's real. It has physical properties. It can be measured. And crucially, according to the laws of quantum mechanics, it can never truly be destroyed. When something happens in the universe, a subatomic particle changes direction. A quantum state collapses from potentiality to reality. A star explodes in a burst of energy. There's a change in information, and that change, that transformation of data, it has consequences. Those consequences are the events we observe. That's why some physicists are now arguing that information is just as real as matter or energy. Maybe, just maybe, even more real. Perhaps matter and energy are just ways that information manifests or is processed. John Wheeler, a giant in 20th century physics who worked alongside Einstein and helped forge the foundations of both quantum mechanics and general relativity, captured this radical idea in 3 deceptively simple words. It from bit. What did he mean by that? He proposed that everything we perceive, every fundamental particle, every force field, every aspect of what we call reality, might ultimately emerge, might be built from simple, binary distinctions, from yes or no questions, from bits. The same kind of fundamental bits that power your computer or phone. Only here, they're not etched onto silicon. They're woven into the very fabric of space and time. This isn't just a poetic metaphor. It's a serious proposal being explored with rigorous mathematics. Think about how any digital system works. You have a set of underlying rules, the code, the algorithm, that processes inputs and produces outputs. In our computers, this happens through physical components called logic gates, manipulating electrical signals. But in the universe, according to this view, it happens through physics itself. The famous equations that describe gravity, electromagnetism, the strong and weak nuclear forces, quantum mechanics. Maybe they don't just describe the behavior of objects moving through space and time. Maybe they describe how the properties of things, their information content, relate to each other and change over time. When a photon of light hits your eye, it's not just a tiny particle bumping into something. It's carrying information, its energy, its direction, its polarization. All of that is data. Your body, this incredible biological system, translates that data into electrical signals that travel along your optic nerve. Your brain processes those signals, and somehow, magically, they become perceptions, thoughts, consciousness. And where did that photon get its information? From the atom that emitted it. And that atom got its information from previous interactions, stretching back and back through time. Every single interaction in the universe, at its core, is a transmission of data. Every force isn't just a push or a pull. It's a way of transferring information from one point or system to another. Even what we label as fundamental properties, like mass or electric charge, might simply be labels for how an object stores and processes information within the cosmic computation. Now, let's imagine zooming all the way down, past the familiar world of atoms and molecules, past electrons and quarks, down, 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 to the absolute smallest possible scale we can conceive of, the Planck scale. This is the realm where our current understanding of space and time literally starts to break down. At this level, some physicists, like the brilliant Carlo Rovelli, propose that space isn't the smooth, continuous stage we experience. It might be granular, discrete. Instead of being an empty void that things move through, space itself might be made up of tiny, indivisible units, like pixels on an unimaginably vast, three-dimensional screen. And time? Instead of flowing like a continuous river, it might tick forward in infinitesimal jumps, like frames in a film reel, running at an astonishingly fast rate. If you look closely at the world around us, from this perspective, it becomes strikingly evident that reality, at its deepest level, seems far more discrete than continuous. Everything appears to follow an underlying algorithmic structure. Think about DNA, that blueprint of life. It's fundamentally a sequence, a biological code built from discrete units, nucleotides. It's a set of digital instructions for building every living thing on this planet. Or consider elementary particles. They aren't just discrete in their existence. They express their fundamental properties, like energy, in quantized, specific packets. Like steps on a ladder, not a ramp. When you strip it all down, the underlying fabric of everything, from genetic code to particle energy levels, appears to be governed by distinct states, by what we might call a cosmic code of zeros and ones, yeses and nos. If that's true, then the universe doesn't just look like a digital system. It is one. In this view, the laws of physics aren't just things we happen to discover through observation and experiment. They are the very source code of the universe. And everything we see, galaxies swirling, planets forming, life emerging, minds thinking, is simply what happens when those fundamental rules run long enough, processing information step by step over billions of years. There's another strange, almost counterintuitive implication here. If reality is fundamentally digital, informational, then it's finite. It can only contain a limited amount of information within any given volume. This isn't just speculation, it's a principle rooted in theoretical physics. There's only so much data you can pack into a specific region of space before it collapses under its own informational weight, often into a black hole. This boundary on how much information a region of space can hold is called the Bekenstein bound, proposed by Jacob Bekenstein. And it's fascinating because it suggests the maximum amount of information isn't based on the volume of the space, as you might expect. It's based on its surface area. This surface area dependence is exactly what we observe with black holes, and it's one of the strongest pieces of evidence pointing towards the informational nature of reality. According to the famous holographic principle, developed partly from studying black holes, the information that falls into a black hole isn't destroyed. It's thought to be encoded entirely on its two-dimensional surface, the event horizon. Just like a 3D image can be stored on a 2D hologram. Taken to its extreme, the holographic principle suggests the entire universe might work this way. What we experience as three-dimensional space, the depth, the volume, the distance between things, could actually be a projection, like a cosmic movie, of data encoded on a distant, two-dimensional boundary we can't directly perceive. Even if the universe isn't literally holographic in that specific sense, the idea that it's fundamentally made of information, not just contains it, becomes increasingly compelling. It explains too much. Why are the laws of physics so elegant and mathematical? Why do quantum states collapse in specific probabilistic ways? Why is there a universal speed limit? The speed of light, which also happens to be the maximum rate that information can travel. It all fits together cleanly in this framework. The universe, it seems, might not be a place where information lives. It might be information living. Now, let's be clear. This is subtly different from the simulation theory you might have heard about. The simulation theory suggests that reality is an artificial construct running on a computer built by someone or something else. Like a character in a video game discovering they're in a simulation. But what we're discussing here is more profound. There is no outside. There is no other system hosting us. The universe isn't on a computer. It is the computer. It is the thing performing the computation. It doesn't need an external observer watching it. It doesn't need a server farm in some other dimension. It simply is what it is. A system that processes information according to its own internal rules, constantly transforming input into output. In other words, when we talk about the universe as a quantum computer, we're not saying it's pretending to be real. We're saying this is what real is. This perspective doesn't instantly change the world you see around you. You'll still wake up tomorrow, make your coffee, probably go to work. The sun will rise. Gravity will keep your feet on the ground. But beneath it all, the particles in your brain, in your coffee cup, in the light from the sun, they are interacting with each other in ways that carry meaning, that transfer data, that build structure. And those interactions aren't just blindly chemical or mechanical, they are fundamentally informational. That means your thoughts, your choices, your experiences, your very sense of self, all of it is built from bits. The same kind of fundamental bits that describe the orbit of a planet or the decay rate of a neutron. You are the output of a process, but not in the way some people pessimistically interpret simulation theory. You're not a puppet. You're not fake. You're just real, in a way we are only just beginning to truly understand. You are a complex pattern of information within the cosmic computation. Now, if we're going to seriously ask whether the universe is a quantum computer, we should probably get a slightly better handle on what a quantum computer actually is. Forget the headlines about them just being faster or magical futuristic machines. That's part of the story, but it misses the point. The real story is about how quantum computers process information, and how that process is fundamentally, utterly unlike anything we've ever built before. Let's start with a familiar, a normal, classical computer. The kind powering your phone, laptop, the internet, works using bits. A bit is the simplest unit of information. It can be either 0 or 1. That's it. Everything your digital life depends on comes down to millions, billions, or trillions of these tiny switches flipping between these two distinct states, on or off, true or false, yes or no. This system is incredibly powerful because it's simple, stable, and predictable. but it bumps against fundamental limits. Some problems are just too complex, with too many possibilities for classical computers to solve in any reasonable amount of time, even with all the computing power on Earth. That's where quantum computing enters the picture. A quantum computer uses qubits, not bits, and qubits don't behave like simple switches. They behave like quantum systems, which means they can do things that seem utterly bizarre from our everyday perspective. For one, qubits can exist in a state called superposition. This means they aren't confined to being just 0 or 1. They can be in a combination of both states at once, with certain probabilities attached to each outcome. Think of a coin spinning high in the air. Until it lands or you catch it, it's not definitively heads or tails, it's sort of both. Or somewhere in between, holding the potential for either result. In quantum mechanics, this isn't just a metaphor. It's a physical reality for these microscopic systems. A qubit can simultaneously represent multiple possibilities. And here's where it gets really powerful. When you have multiple qubits working together, the number of possible states they can collectively represent doesn't just add up, it grows exponentially. 10 classical bits can represent only one of 1,024 possible values at any given moment, from 000000000, 0 to 1,100,000, 11,100,000, 11,100, 11. But 10 qubits? Thanks to superposition, they can effectively represent all 1,024 values simultaneously. This gives quantum computers an almost unimaginable level of parallelism. They're not just trying one solution after another like a classical computer. They're exploring vast landscapes of possibilities all at once. Then there's entanglement. When two or more qubits become entangled, they become interconnected in a profound way. The state of one instantly influences the state of the other, no matter how far apart they are. Measure one entangled qubit, and the state of its partner is instantly determined, faster than the speed of light. Einstein famously called this spooky action at a distance, and it still boggles our minds today, but it's been demonstrated repeatedly in experiments. And it's a key part of how quantum computers work. Entanglement allows qubits to work together in incredibly sophisticated, correlated ways that classical bits simply cannot replicate. They don't just store and process information individually. They share and interweave it across their entire entangled system. This capability enables computations that are massively more efficient for certain types of problems that map well onto quantum mechanics than anything classical systems can achieve. But this quantum power comes with a huge caveat. It's incredibly fragile. Quantum systems are notoriously sensitive to their environment. Any disturbance, heat, vibration, stray electromagnetic fields, or even just the act of observing them too directly, can destroy the delicate superposition or break the precious entanglement. This is why building a stable, useful quantum computer is one of the hardest engineering challenges humanity has ever faced. You need to isolate these qubits almost perfectly, control them with exquisite precision, and keep them stable long enough to actually run a meaningful calculation. We're getting better, but we're still in the very early stages. So, that's the basic picture of quantum computation. Harnessing superposition and entanglement to perform calculations that are impossible or impractical classically. But what does this intricate, fragile technology have to do with the vast, seemingly robust universe? Well, go back to the fundamentals of quantum mechanics itself. At the microscopic level, everything behaves like a quantum system. Particles don't have definite positions or velocities until we make a measurement. They exist in a spread of possibilities, a kind of quantum blur, a superposition of states. And when they interact, they don't just bump like billiard balls. They interfere with each other like waves. They become entangled. Their superpositions collapse into definite states. In short, they compute. And that's the key, profound idea. A quantum computer doesn't simulate quantum mechanics the way a classical computer might run a simulation of weather patterns. A quantum computer is quantum mechanics. It doesn't fake the rules, it runs on the rules. That's why quantum computers hold such immense potential power for certain problems. Because the universe itself, at its most fundamental level, is already quantum. So, when you build a quantum computer, you're not building a tiny model of reality. You're building a machine that plays by the same fundamental rules reality itself already follows. This is why the idea of a quantum universe, a universe as a quantum computer, is gaining traction. Not because it's a convenient or trendy metaphor, but because it might offer a unifying framework to explain why the laws of physics look the way they do, why reality has such deep mathematical structure, why events follow discernible patterns, why entropy tends to increase, why time seems to move forward. All of these features, the flow of information, the probabilistic change of states, the interconnectedness of distant events, the irreversible outcomes of measurement, these are core features of computation, particularly quantum computation. So the question isn't really, could the universe be a quantum computer? The more pressing, perhaps unsettling question is, given how reality behaves at the deepest level, what else could it be? It's one thing to speculate, to say, maybe the universe is a quantum computer. It's another entirely to look at the cutting-edge science, at the deepest mysteries physicists grapple with, and find signs that this might actually be true. This isn't just about clever analogies anymore. It's about mathematical models, testable theories, and real hard work by researchers that gives this radical idea some scientific traction. Let's start with something profoundly strange that's puzzled the sharpest minds for decades: the black hole information paradox. This problem emerged when Stephen Hawking, in a groundbreaking calculation, showed that black holes aren't perfectly black. They slowly evaporate over unimaginably long timescales by emitting particles and radiation, now known as Hawking radiation. But here's the critical issue. This radiation seems to be completely random, carrying no information about what fell into the black hole. If a black hole eventually evaporates completely, and all that's left is this seemingly random radiation, what happened to the original information? Did it just vanish? Quantum mechanics has a fundamental rule. Information cannot be destroyed. It can be transformed, scrambled, hidden, but not erased from existence. So, if black holes destroy information, they break a core law of quantum mechanics. But if they don't, where does the information go? This is where the quantum computing perspective offers a potential way out. A black hole, some researchers propose, might be acting not just metaphorically, but literally, as a quantum information processor. An actual quantum system that takes incoming information, encodes it, perhaps scrambles it into a highly complex entangled state, but crucially, doesn't erase it. When the black hole evaporates via Hawking radiation, it doesn't destroy the data. It releases it. It comes out. But in a highly scrambled form, embedded in the subtle quantum correlations of the outgoing radiation. In fact, some physicists now theorize that black holes are among the most efficient scramblers of quantum information in the known universe. The bizarre extreme physics of black holes might only make sense if we treat them as actual quantum computers, performing complex operations on infalling data. And it's not just black holes. More and more researchers are pointing to quantum entanglement, that spooky action connection between particles, as the fundamental glue holding everything together, including space itself. Some cutting-edge theories now propose that spacetime itself, the arena of the universe, might actually emerge from patterns of entanglement between fundamental quantum bits. A leading figure exploring this idea is Mark van Ramstonk. His influential work, particularly his 2010 paper, Building Up Spacetime with Quantum Entanglement, makes a compelling argument. The connectivity and geometry of spacetime appear to be intimately tied to the entanglement of underlying quantum degrees of freedom. The more entangled two regions of space are, the closer they seem to be. If the entanglement between them is reduced or broken, those regions effectively drift apart. The idea is radical. Space isn't fundamental. It's built from these fundamental quantum bits that are entangled in specific, intricate patterns. If the pattern of entanglement changes, the geometry of space and time changes along with it. Think of it like stitching together a cosmic fabric. The more tightly two threads are stitched together, the more entangled they are, the closer they appear in the fabric. If you cut those stitches, the space between those threads grows. This view completely flips our traditional perspective. Instead of space containing information in the form of entanglement builds space. This model isn't just a nice philosophical picture. It's being rigorously tested using advanced mathematical tools. Tensor networks like MERA, multi-scale entanglement renormalization ansatz, are mathematical structures physicists use to describe complex entanglement patterns. When you construct a system using MERA and evolve it, you don't just get abstract information. You get a geometric structure that surprisingly looks like curved spacetime. It's a powerful hint that quantum computations aren't happening inside spacetime. Spacetime might be emerging as a result of those computations. Another fascinating area pushing this idea forward is quantum error correction. As we discussed, qubits are incredibly delicate. They can easily lose their quantum state, their superposition or entanglement, if they interact with the noisy environment. To build reliable quantum computers, we need sophisticated error-correcting codes that can preserve quantum information by spreading it out, encoding it across multiple qubits so that errors in one or a few don't corrupt the whole. Intriguingly, physicists are discovering deep, unexpected connections between the structure of these quantum error-correcting codes and the structure of spacetime itself, particularly in models like ADS, CFT, anti-de Sitter, conformal field theory, which relates gravity in a certain type of spacetime to a quantum field theory on its boundary. Some models of ADS, CFT, can be described as quantum error-correcting codes. This suggests that the universe itself might be using similar codes, cosmic error correction, to preserve its fundamental information. Every region of space might contain quantum information, but this information isn't stored in a single fragile location. It's spread out, redundantly encoded through vast patterns of entanglement. Even if some parts get corrupted, maybe near a black hole or due to random quantum fluctuations, the overall information, the structure of reality, is protected by an underlying code, like a cosmic firewall preventing errors from destroying the system. In other words, the geometry of spacetime itself might literally be a quantum error correction system, a brilliant, fundamental way for the universe to compute and evolve without immediately breaking down into noise. And let's not forget the inherent weirdness of quantum mechanics itself. Every time we run an experiment with entangled particles, every time we see the baffling interference patterns in a double-slit test, even when sending particles one at a time, we're watching information behave in ways that only make sense if something deeper, something fundamentally quantum and computational, is being processed. The core rules of quantum physics, superposition, measurement, entanglement, interference, aren't just abstract oddities dreamt up by theorists. They are the exact same rules that power laboratory quantum computers that scientists are already building. And the more we understand how these small-scale quantum systems work, the more the vast universe starts to look like a scaled-up, immensely complex version of that same underlying quantum logic. So, we have black holes acting like the universe's fastest information scramblers, consistent with them being quantum processors. We have the holographic principle hinting at information compression. We have the structure of spacetime potentially emerging from entanglement, and we have quantum error correction showing up in our most advanced models of reality. These aren't just isolated curiosities. They are pieces of a gigantic, profound puzzle. These pieces don't give us the full picture yet, not by a long shot. We still need a complete, unified theory of quantum gravity. We don't fully understand how spacetime, geometry, and fundamental computation relate on the grandest scales. But the clues are undeniable. And the more we look, the more it seems like the things we thought were solid, fundamental building blocks, particles, space, time, might just be the output, the emergent phenomena of something far more fundamental. Information, logic, computation, not happening in the background, but as the background itself. If the universe is a quantum computer, then the way we've conventionally thought about physical laws might be profoundly incomplete, not necessarily wrong, but backwards. Instead of the universe being a passive machine that obeys fixed, external laws like a robot following programmed instructions, perhaps the laws themselves are a product of the computation, They aren't external rules imposed upon the system. They are the internal logic that emerges as the system runs. That means we shouldn't necessarily think of gravity, electromagnetism, and the strong and weak nuclear forces as entirely separate pieces of cosmic machinery. Instead, they could be different layers of processing, distinct subsystems within a larger, unified algorithm. Maybe they only appear distinct to us because we're zoomed in too far, like looking at a digital image on a screen and only seeing the individual pixels, rather than the complex, integrated image they form together. So here's one way to frame it. What we call the laws of nature are simply the rules, the patterns that remain consistent and stable across the longest, running, most robust parts of the computation. They are emergent properties, not imposed decrees. And if that's true, then some laws might not be absolute, universal constants after all. They might subtly shift or behave differently under extreme conditions. Say, in the scorching density of the early universe, inside the crushing gravity of a black hole, or perhaps at the distant edges of the observable cosmos. They might even be different in other regions of a much larger, interconnected quantum system. Call it a multiverse if you like, but not in the sense of bubble universes floating in nothingness. More like different sectors of a vast, continuous informational structure, running slightly different versions of the cosmic rulebook. This perspective also fundamentally changes how we understand energy. Traditionally, energy is the capacity to do work, to move matter, to cause change in physical systems. It's a property of the machine, but in information theory, energy isn't just fuel, it's deeply intertwined with information processing itself. The famous Landauer's principle shows that erasing a bit of information fundamentally requires a minimum amount of energy dissipation. Processing information consumes energy. If the universe is constantly performing this colossal computation, then maybe the Big Bang wasn't just the sudden appearance of matter in space. Maybe it was the ultimate boot-up event. A surge of usable energy, of available computational resources, if you will, that made large-scale quantum processing and the emergence of complex structure possible. That gives a different, maybe even hopeful, meaning to thermodynamics. The second law, which states that entropy, often associated with disorder, always tends to increase in a closed system, might just be a description of the universe exploring more and more possible configurations of information over time. It's not just getting messier in a simple sense, but expanding its state space, spreading its information across an increasing number of possibilities. What appears to us as increasing disorder or randomness might simply be information becoming distributed, becoming less localized, perhaps simply information not yet understood by us. And that brings up one of the most profound speculative questions of all. What is the purpose of this computation? Not purpose in a mystical, "why are we here?" sense, but in a scientific or computational sense. Is the system optimizing for something? Is it computing towards a particular state or goal? In our computers, we write programs to solve specific problems, but in nature, the problem might be open-ended. Maybe the universe isn't trying to solve anything in our human sense. Maybe it's just running, exploring the full, almost infinite range of outcomes possible under its foundational rules. Or maybe, just maybe, it's biased towards complexity, not by conscious design, but by statistical tendency. Think about it. From the formation of the very first atoms, to the ignition of stars, to the complex chemistry that led to life, and eventually to the emergence of conscious awareness, complexity has relentlessly emerged and increased over billions of years. This doesn't break the laws of entropy. It works within them, creating local pockets of order in a system where overall disorder is increasing. But it shows that complexity doesn't just survive in an information-rich, dynamic system. It thrives. It arises naturally because the universe's particular way of processing information, governed by its rules, seems to statistically favor interaction, feedback loops, and self-organization. Structures don't just appear randomly. They reliably unfold from simpler states when the underlying information flow allows it. Could it be that the universe's ongoing computation naturally leans towards maximizing complexity? Not as an intended goal, but as the most probable statistical result of how information is processed according to its specific source code? If so, then life, thought, intelligence, None of this is a cosmic accident in the sense of a random fluke. It's what tends to emerge. It's what's arguably inevitable when enough information flows through enough computational steps over enough time. They are intricate patterns that appear again and again in a system that favors the recursive, the interactive, the ever-growing. And that reframes our place in this cosmic algorithm, doesn't it? We're not separate observers standing outside, watching a cosmic machine tick along. We are part of the machine. We are made of the same fundamental informational processes. Our thoughts, our feelings, our consciousness, they are just as much a product of quantum interactions and informational processing as the force of gravity or the glow of a distant star. But we are unusual, perhaps unique as far as we know. We are part of this system that can reflect on itself. Our awareness, whatever its ultimate nature, is one of the few known structures in the universe capable of modeling, questioning, and trying to understand the very rules that created it. That might be the rarest thing in the universe. Not life itself, not even intelligence, but self-reference. The ability of a process to loop back and study the larger system to which it belongs. In a purely classical, mechanical universe, that kind of self-awareness might seem like an inexplicable anomaly, but in a quantum computational one, it's not entirely surprising. Recursive systems, programs that analyze or even write other programs, systems that model themselves, these happen all the time in computing. Maybe what we call science, what we call our quest for understanding, is simply the universe's way of iterating on itself, testing hypotheses, refining its models, revealing its own internal logic through minds embedded inside the very process they are studying. So, what would it truly mean if the universe is a quantum computer? It means we are not standing at a distance, observing a machine from the outside. We are the machine, studying itself, line by line, bit by bit. Once you start seriously thinking about the universe as a quantum computer, a very specific, almost unavoidable question comes up. If this is all computation, could we simulate it? Could we, from within this universe, build a machine, maybe even a quantum computer, that could perfectly mirror the entire universe? It sounds like a logical next step, right? After all, we already build simulations of reality all the time. Physicists create computer models of galaxies colliding, black holes forming, or how complex molecules interact. We use equations to recreate the paths of planets or the evolution of stars. And with quantum computers slowly advancing, we're beginning to simulate small, actual quantum systems accurately. So, if the universe is fundamentally running on a quantum engine, why couldn't we build our own, one that could mirror the whole thing? But here's where we hit a hard, almost philosophical wall that's rooted in physics itself. Simulating a system from within the very system you're trying to simulate is fundamentally limited. There are hard constraints, not just about our technological capability, but built into the laws of physics and logic. To start, there's a basic principle from computer science and information theory. No system can perfectly, completely, and with full detail simulate or model itself. This isn't just a philosophical musing, it's mathematically demonstrable in certain contexts. If you try to build a perfect one-to-one model of something as large and complex as the system you are a part of, that model would inherently require as much or even more memory, processing power, and fundamental resources than the original system it's trying to copy. And since your model exists within the system you're trying to simulate, it can never logically exceed the system's total capacity. It's a kind of reflexive limitation. A mirror can't reflect itself entirely. A book can't contain a perfect full-size copy of itself inside its own pages. There's always a part, the part doing the observing, the part holding the copy, that can't be fully included in the copy itself. And in physics, this idea shows up in more than just abstract logic. It appears in the limits imposed by thermodynamics, in the maximum information density allowed by gravity, like the Bekenstein bound, and even in the inherent uncertainty of quantum theory itself. The Bekenstein bound, remember, tells us there's a finite amount of information in any given volume, limited by its surface area. If you tried to create a perfect simulation of the entire universe, every particle, every field fluctuation, every quantum state, you'd need to store an unimaginable amount of information. But where would you store it? Inside the universe? That's trying to fit a container inside itself, and you'll always, fundamentally, come up short. This puts a fundamental physical limit on how much of the universe can be simulated from inside the universe. You can model parts of it. You can build approximate simulations, simplified versions focusing on specific phenomena. But a full, perfect one-to-one replica? It's not just technologically challenging, it's physically impossible within the framework of these laws. Not unless you're okay with leaving parts out, simplifying, averaging, or using statistical shortcuts that lose the fine-grained detail. But what about quantum computers specifically? They are different. They don't simulate quantum systems the way classical computers do, by writing equations that approximate quantum behavior. They are quantum systems. This gives them a unique kind of native compatibility. You can represent certain quantum interactions much more efficiently, process entanglement naturally, and perform computations that would be impossibly slow for classical systems. But they are still bound by the same underlying laws and limits. A quantum computer with 100 qubits might be able to perfectly simulate certain quantum systems with 100 particles. But simulating every qubit, every fundamental degree of freedom, in the universe? That would require a quantum computer as large and complex as the universe itself. And, again, we hit the self-simulation limit. A system cannot perfectly contain a model of itself. There's always a boundary you can't cross from the inside. Still, acknowledging this limit doesn't make the effort meaningless. You don't need a perfect simulation of the whole thing to learn something incredibly useful about how it works. That's what science has done for centuries. It builds models. Simplified, imperfect models that capture essential aspects of reality. When we study planetary orbits, we often ignore air resistance or the gravitational pull of distant stars. When we study thermodynamics, we simplify billions of molecules into statistical properties. In quantum physics, we study isolated, idealized systems. Two entangled particles here, a single atom interacting with light there. Not because these are perfect representations of complex reality, but because they help us isolate the fundamental rules, the basic logic, and understand how it operates. So, if the universe is a quantum computer, and we are part of it, then maybe our ultimate job isn't to build a perfect replica of the whole thing. Maybe it's to identify the patterns, to isolate the small, repeatable computational structures, to reverse engineer the cosmic logic piece by piece. We don't need to build a second universe to understand the first. We just need to trace the pathways of information, step by computational step, and figure out what kinds of patterns are stable, what kinds lead to collapse or change, and what kinds ultimately produce the astonishing complexity and consciousness we see all around us. That might sound modest compared to simulating everything, but it's profoundly powerful. Consider this. We already know that parts of the universe, many natural processes, are computationally irreducible. That means there is no shortcut, no clever mathematical formula that can predict the outcome without actually running the process. That's why precisely predicting the weather weeks in advance is impossible. That's why the future of truly chaotic systems remains fundamentally out of reach. If the universe really is running as a cosmic computation, then fully understanding its future doesn't mean just solving a static equation. It means understanding the computation itself, how input becomes output, how states evolve, how the algorithm unfolds. Could we ever simulate that completely? Probably not, because of those inherent limits. But that doesn't mean we're stuck. In fact, it suggests that partial simulations, small, focused quantum models, might be our most powerful tools for probing the universe's deepest workings. They already are. Researchers are using small quantum processors to simulate the behavior of molecules in chemistry, model exotic materials in condensed matter physics, and even explore simplified versions of quantum gravity or black holes. These aren't just academic exercises. They are windows into the underlying rules, giving us glimpses of the cosmic source code in action. And there's one more fascinating angle worth considering. If we can't simulate the universe completely from the inside, can the universe simulate us? In a strange, almost circular twist, it already does. Every particle interaction within our bodies, every biological process, every flicker of neural activity in our brains, They all play out according to the fundamental rules of quantum mechanics and information transfer. We are already being simulated, in a sense. Not artificially, not in some foreign system, but as an intricate, complex, self-organizing subprocess running within the cosmic computation itself. We are subprocesses in the larger algorithm, constantly running, updating our states, reacting to inputs, producing outputs, reflecting on the process. So maybe the ultimate goal isn't to build a separate machine to replicate the universe. Maybe the goal is to recognize that we are already embedded in it, not just as passive observers, but as active, conscious computations. As structures that have, by some strange miracle of complexity, gained the ability to study the rules, to adapt to them, and perhaps even to subtly influence the ongoing computation through our actions. Our discoveries, our thoughts, our questions. Like this one. If the universe is a quantum computer, then it must ultimately obey the same fundamental limits as any other system that processes information. And that means, sooner or later, perhaps on timescales almost beyond comprehension, it can't compute forever in the same way, not at the same level of complexity. At some point, every computation, every system runs into constraints. Energy is depleted, memory resources become saturated, the system reaches a stable limit, and the process either halts, slows down dramatically, or possibly breaks apart into simpler components. So, if the universe is computing its own evolution, what happens when the fundamental resources it needs to sustain complex computation, usable energy, low entropy states, coherent order, start running low? This isn't just a bleak philosophical forecast. It's already written into the fundamental laws of thermodynamics. The second law tells us that entropy, a measure of disorder or the dispersal of energy, tends to increase over time in any closed system like our universe, at least the observable part. In the language of information, this means that usable energy, concentrated in gradients and structures, like stars or chemical bonds, is gradually converted into unusable energy, heat spread out uniformly. Noise. Systems naturally move from highly structured, low-entropy states to increasingly random, high-entropy states. And from a computational perspective, this means the process becomes less and less interesting. Without usable energy gradients, complex computation stops. Right now, stars shine because they are converting concentrated nuclear fuel into diffused energy. Planets orbit because of gravitational potential and kinetic energy. Living systems function because they convert chemical energy into ordered structure and activity. But all of these processes are part of a one-way path. Gradually, energy is being spread out, locked away in unusable forms, lost to the background noise. Physicists call the likely ultimate end state of the universe the heat death, a time perhaps trillions upon trillions of years from now, when everything is so spread out, so uniform in temperature and energy distribution, that no work can be done. No stars burning, no planets moving, no chemistry, no life. From a classical perspective, that's already profoundly bleak. But from a computational one, it might be worse. It means the system will still exist, but it won't be doing anything meaningful in terms of generating new complexity or processing interesting information. A frozen computation, a vast, silent machine, still technically on, but with nothing left to calculate, nothing new to output. This raises questions we usually shy away from. If the universe is a quantum computer, is it already degrading? Are we living in a particularly active, perhaps rare, phase of the computation? A temporary surge of complexity and information processing before a long, inevitable descent into inactivity? Cosmologists struggle to estimate the timescale of this cosmic slowdown. Some suggest trillions of years before the last stars flicker out. Others imagine timescales so vast that even black holes will eventually evaporate via Hawking radiation, leaving behind nothing but the most diffuse radiation. But even long before that ultimate state, the rate of complex computation, the generation of new structures, new events, new outcomes, will begin to drop. The system will slow down. This doesn't mean the universe will suddenly turn off in a dramatic crash. It means change will stop being interesting. If there are no more energy gradients, no more significant differences in state, then nothing can evolve in complex ways. Without contrast, there's no computation of interest, just repetition or static uniformity. A cosmic loop with no feedback, no progress. And what happens to the information? Quantum mechanics says it can't be destroyed, only transformed. So, if all the computation slows to a crawl and energy disperses uniformly, where does all that stored information go? Is it locked within the quantum states of incredibly diffuse, frozen particles? Encoded in the subtle, static structure of near-empty space? Some physicists believe it might still be preserved, in principle, even if it becomes utterly inaccessible, like data on a hard drive buried under miles of rock with no power source. Still there, still part of the system's history, but inert, unreadable, trapped within the unchanging end state. Others suggest that information might somehow loop, not in a simple repeating cycle, but in a thermodynamic sense. That given truly infinite time, even the smallest, random quantum fluctuations might eventually, against all odds, momentarily recreate pockets of complexity. This is where the concept of Boltzmann brains comes in. Hypothetical, isolated observers that might spontaneously form out of the thermal chaos in the far future, briefly experience awareness, and then dissolve back into noise. It's not a comforting thought. It points to a universe where meaning and consciousness emerge rarely, unpredictably, and fleetingly before being reabsorbed by the overwhelming dominance of noise. There's another possible implication, perhaps even darker. A structural failure. In digital systems, when memory resources are exhausted or a process encounters a fatal error, you sometimes get a system crash, a breakdown, a forced halt, or even a hard reset. Could something like that happen at cosmic scales? Is there any scenario where the computation doesn't just fade slowly but ends abruptly, or shifts into a fundamentally different mode? That's harder to answer with confidence. We don't know if the universe's algorithm has any built-in halting mechanisms. Currently, the expansion of space appears to be accelerating, not slowing, suggesting a stretch towards cold emptiness rather than a collapse. But if something fundamental about the computation changes, say a phase transition in the vacuum state itself, or a breakdown of the physical laws we currently observe at extreme energies, the system could undergo a radical change, a reboot, a shift to a new computational mode with entirely new rules, new physics, a clean slate, like flipping a switch on the underlying reality. This possibility, sometimes called vacuum decay, is highly speculative, but it's a stark reminder that the source code we currently observe, the laws of physics we measure, might not be eternal constants. If they are expressions of an ongoing computation, and the fundamental parameters or states of that computation shift, then reality as we know it could quite literally dissolve, not because of violence or destruction, but because the system no longer supports the logic that defines our version of reality. And if that's true, then what we call existence might not have a firm, singular edge. It could be just one phase in an endless process of information being organized and reorganized in different forms. Structure giving way to noise, noise giving birth to structure, complexity emerging and then dissolving again and again across vast cosmic cycles. So the potentially dark implication isn't just that the computation could stop, it's that it might keep going without us. Without consciousness, without memory, without any of the emergent complexity that makes it interesting from our perspective. Just pure information unfolding meaninglessly like a broken loop no one can watch. A process that persists simply because the underlying logic continues to run, not because anything drives it forward with purpose, but because nothing prevents it from continuing its basic operations. And yet, even that has weight. Because right now, in this thin, fleeting slice of cosmic time, the computation is active. The gradients are still here. Structure is still forming. Complexity still emerges. The universe is still doing something. And that's the piece we, lost in our anxieties about the end, tend to miss. If the quantum universe really is a computation, then meaning might not be some inherent property built into the machine from the start. It might be something that arises dynamically during the rare temporary phases when complex structure and self-awareness exist, like now. It may not last forever, but for now, it's real. And maybe, just maybe, that is enough. After all the theories, all the analogies, all the careful modeling, all the peering into black holes and quantum entanglement, we're left with a question that doesn't get asked nearly often enough. Is this it? Not, is this all there is, in a pessimistic sense, but in a serious, scientific one. If we've followed the thread this far, if we've stripped reality down to quantum logic, to informational flow, to the rules that make the rules, then how much deeper can we actually go? How much more fundamental can our questions be before they stop being answerable from within the system? Thinking of the universe as a quantum computer offers a remarkable degree of clarity and coherence. It gives us a single, consistent picture where everything, from the smallest particle to the largest cosmic structure, is made of the same basic stuff, information, processed according to quantum laws. It provides a potential explanation for the strange, non-intuitive behavior we see in nature. The probabilistic outcomes, the instantaneous entanglement, the wave-like interference, the fundamental limitations on what we can measure simultaneously. These don't have to be seen as bizarre glitches. They are features of the system, what you'd expect from a computation unfolding at the most fundamental quantum scale. And unlike older metaphors, this one doesn't position us as external observers. We're not watching a cosmic machine from a distant, detached viewpoint. We are within it. We are subprocesses embedded within the very logic we are trying to decode. That makes this view personal, not in a vague, mystical way, but in a deeply structural one. We are part of the computation trying to understand itself. So maybe, just maybe, this is the most useful lens we've found so far. Not necessarily the absolute, final truth, but the clearest, most consistent framework that connects physics, computation, complexity, and our own experience. It simply asks, what if everything is information, and everything evolves by the fundamental rules that information follows at the quantum level? But accepting this perspective also sets a boundary. Because if the universe is a computation, then there are almost certainly things we may never know. Not because we're not clever enough, or haven't built big enough telescopes, but because some things are fundamentally unsolvable or unknowable from inside the system. We know from mathematics and computer science that some problems have no solutions. Some questions are fundamentally undecidable within a given system. Limits exist, and we might be brushing up against them. We might never answer what started the computation, or why it started. We may never know for sure what, if anything, lies beyond this cosmic computational structure. We might reach the most fundamental layer we can access and realize that the bottom of the stack isn't made of tiny solid things or swirling energy fields, but logic, structure, information itself. And maybe that's okay. Maybe asking for more than that. Asking for a built-in meaning, a grand narrative dictated from outside, a fundamental substance beneath the rules, is a leftover habit from older ways of thinking. The quantum computer view doesn't necessarily offer comfort. It offers coherence. It doesn't explain why we are here, but it does offer a powerful framework for understanding how the system behaves while we are. And maybe that's what makes it both unsettling and profound. There's no pre-programmed purpose in this view, no built-in destiny. Just a set of rules, an evolving set of states, and the rare, precious emergence of structure, complexity, and self-awareness along the way. Still, within that vast, potentially impersonal process, there is something undeniably strange and precious happening right now. A brief, active phase on one small planet, in one corner of the system, where fundamental particles arrange themselves in such intricate ways that they became aware of the computation. They began to study it, question it, build models of parts of it, and even discuss its very nature. And that's where we are. We are quantum systems, shaped by the flow of information, reflecting on the process that shaped us, using the very tools and logic given to us by the system, our minds, our science, our curiosity, to ask what the system itself is. It might not be the simple, comforting answer we perhaps hoped for, but it might just be the most honest, most accurate one we are capable of reaching from inside the cosmic algorithm. So, what does any of this mean for us? Right here, right now. If reality is this incredible, ongoing quantum computation, it means every moment we experience is a real output of that process. Every connection we make, every thought we have, every act of creation or understanding, it's not happening in some fake simulated world. It's part of the universe doing its thing. It's the computation unfolding. Maybe the lesson is to appreciate the activity, to cherish this phase of complexity, to find meaning not in some external, dictated purpose, but in the very act of processing information in complex, beautiful ways. In learning, creating, connecting, loving, exploring. These aren't just things we do. They are incredible examples of the cosmic computation producing astonishing, self-aware outputs. It reminds us that even if we are made of instructions, those instructions have, through billions of years of processing, resulted in consciousness, choice, and the capacity for wonder. We are not just lines of code being run. We are the moments where the code becomes aware of itself, where it asks questions, where it feels. So, next time you look at the stars, or marvel at the complexity of a living thing, or even just ponder a difficult problem, remember that you are witnessing and participating in the most incredible computation imaginable. You are a part of the universe, processing itself. What do you think about the universe as a quantum computer? Does this idea resonate with you, or does it feel too strange? Let me know your thoughts in the comments below. I'd love to hear your perspective on this mind-bending possibility. Thank you for joining me on this journey through the cosmic algorithm. I hope it's given you something fascinating to ponder. Stay curious, keep questioning, and most importantly, please take good care of yourself and your loved ones. Stay healthy. If you enjoyed this exploration, please consider subscribing to the channel and hitting that notification bell so you don't miss our future dives into the deepest mysteries of science and reality.